Not long after Galaxy's Edge opened up in California, the Dead Bothan Society figured out how to read the RFID tags in kyber crystals, and they got their hands on a bunch of different kyber crystals, and they scanned them all in, and they started making a list of the numbers that they were pulling off of the kyber crystals. And what they discovered were that the numbers were sequential, except there were 2 gaps in that list. There were 2 missing numbers that they hadn't encountered. So they did what anybody would have done. They took a kyber crystal and modified it with one of those missing numbers. And what they discovered when they put it into their Savvy's Workshop lightsaber hilt is that this window here, which would normally blink the color of your kyber crystal, started to blink cyan and orange, depending on which number they used. This seemed to imply that the hilt could support cyan and orange kyber crystals, which don't exist as far as we know. So the next thing they did is, of course, put a blade into the hilt, turned it on, and discovered... The discovered cyan would ignite the blade blue, and an orange crystal would ignite the blade yellow. That was a bit odd. They did some further digging and were able to figure out the commands that the hilt sends to the blade. And they could see that the commands to turn on as cyan or orange were also being sent to the blade. So the problem with supporting cyan and orange blade colors and kyber crystals wasn't the hilt. The hilt supports it. The problem was in the blade. In the base of a Galaxy's Edge lightsaber blade, there is a tiny little PCB, and on it there is a microcontroller. That microcontroller's job is to interpret the commands coming into the blade from the hilt, and then to control the LEDs in the blade using these transistors to turn them on and off. For whatever reason, the code that is running on this microcontroller does not include support for cyan and orange colors. Well, it seems like somebody needs to fix that. And it turns out the Dead Bothans thought the same thing. And so what they did is they took a blade apart, they gutted the electronics, they removed the controller, they removed the LEDs, and replaced it with their own. They put inside of the blade a strip of neopixels, and in the base here, an Arduino. And they're using that to control the neopixels and interpret the commands coming from the hilt. And it ignites the blade in a very nice, very smooth action, and now the blade supports cyan and orange colors. And if you want your own blade that can support cyan and orange colors, you can go to the Dead Bothans Society Patreon page, become a Patreon of theirs, and you will get access to build instructions and code so that you can make your own NeoPixel blade based Galaxy's Edge lightsaber blade. So if you want a Galaxy's Edge lightsaber blade that supports orange and cyan colors, become a Patreon of the Dead Bothan Society and use their build instructions and code to make your own. Job done, end of story. But that's where mine begins. For whatever reason, that solution didn't sit well with me. It required a battery and a charge circuit to be added to the base of your lightsaber blade because the neopixels draw so much power it needed the extra battery. I also didn't like the idea of getting rid of everything that was inside the blade. I felt like there should be a simpler solution that keeps the LEDs and maybe just replaces the logic board. The logic board itself really isn't that complicated. All the logic board really is a microcontroller hooked up to 7 transistors and 1 data pin. And that's it. All the code needs to do is interpret the commands coming from the hilt, and then to turn these transistors on and off appropriately to set the color in the blade. With absolutely no experience in doing anything like this at all, I went and designed my own replacement logic controller for a Galaxy's Edge lightsaber blade. And for the most part, I think this would have worked. I don't think the wiring or the layout is a problem. The only issue is how I program the microcontroller. I put these pads on the back of the PCB here, and in my head I would just connect some wires up to them temporarily to program it, and then remove the wires and I'd be all set. The problem is I've hooked up the wrong wires here. I can't program the microcontroller when it's connected to this PCB. So I would have to pre-program it somehow and then solder it to this board. And that was going to be a lot more work and a lot more difficult than I anticipated. So I put this project on hold for a while. About 9 months later, I came back to the project. I revisited my design and modified it slightly. I'm still using the same voltage regulators, the same transistors, the same capacitors. All the components that I was going to use for the first design, I am reusing with this design. I've also figured out what pins I should have on the back, and I've made sure they're wired up correctly, and they're in a form that I can use a fairly standard device to program it with. And this is what an assembled board looks like. I'm using an ATmega 328P, which is the same microcontroller used in most Arduino projects. So I've taken one of these and installed it into a blade. And now, when I put, say, an orange kyber crystal in here, and we can see it blinking orange there, and I turn it on, I get an orange blade, which to you looks a little bit yellow because the camera needs to be helped to see color. That's about as good as it's going to get. But to my eyes, that is a very orange color. And there's no mods in terms of wiring up or cross-wiring different colors in the blade. This is my controller respecting the orange and cyan commands. And in fact, if I grab that cyan-coated red crystal that I have here, we can see it blinking cyan. And I don't really need to do anything to help the camera see that that is a cyan-colored blade. It works great. Job done. Except it's not. When I designed this PCB the first time around, I really didn't have much of an idea of what I was doing. When I designed this PCB, I had a little bit of an idea of what I was doing. But I've learned since assembling this and trying to get the code running on it to control the blade that I still have a little more learning to do. Galaxy's Edge lightsaber blades are designed so that people, when they use them, they look good, but also when they take pictures or video of the lightsabers in action, that they still look good. Mine, not so much. Let me demonstrate that real quick. I've built into my blade, or I should say I've programmed my blade controller to do some extra stuff. I've added extra modes to it. So for example, turn it off and on again real quickly and the blade flickers a little bit. It's like a sort of Kylo Ren's unstable blade effect. And in fact, I came up with a second version of it where individual segments flicker differently. Each blade has 4 segments of LEDs in it, and you can control the whole blade as one big segment, or you can control each segment individually. And in this case, I'm flickering each segment individually. And in person, I think it looks fantastic. But then I've added a few more modes, because the idea of being able to control the individual segments offered some interesting ideas or possibilities. So now I'm going to quickly go through a bunch of different modes here to get into a mode that's going to really demonstrate where my problem is. So here we have a mode that I have always secretly wanted to include ever since the idea of a custom controller came across my mind, which is to have a blade that sort of mimics the colors of a rocket popsicle. Now, with my light on here, everything looks nice, if washed out a little bit. I'm going to adjust the colors now on the camera. I'm going to turn off the light here. Things are going to look a little bit different, and you're going to get an idea of my problem. So I'll show you the colors again. They're more vivid and brighter in person than what you're seeing right now. But the colors aren't the issue. You should be able to see it quite clearly now on the camera. It's that banding effect that you see. These sort of dark lines that seem to be moving up the camera. That's my problem. And it's a problem that the stock Galaxy's Edge lightsaber blades handle with very easily. It's a problem that I, in my current controller's setup, can't handle very well. I'll explain what's going on here. There's a technique for controlling LEDs called pulse width modulation. It's used in a lot of other areas as well, but the idea is basically to turn the LED on and off very rapidly. So if this represents 0 volts, and then it turns the LED on, so this represents the LED being on for a little while, and then it turns off, and then it turns on again, and then it turns off, and so on and so forth. Now the ratio of on to off is referred to as the duty cycle. It's given in as a percentage here. So let's say this is one period. Okay, one on period and one off period together. We'll call it just one period. And let's say this is on 40% of the time. This signal has a 40% duty cycle. And what that means is if the LED is on 40% of the time, the LED will look like it's at 40% of its maximum brightness. And if you turn these LEDs on and off very, very quickly, so quickly that the eye can't see the LEDs turning on and off, then the eye will look at it, will see instead we'll see a dim color instead of an LED flickering on and off. And so you can change that duty cycle 10%, 90%, 100%, whatever you want, and you will change the brightness of that LED. So using PWM to control the red, green, and blue LEDs, we can create a whole range of different colors. Lots of red with a little bit of yellow gives you, something orange. Lots of green, say, but a little bit of blue, that might give you aquamarine. And the way you can give only a little blue but a lot of green, for example, the duty cycle for the green channel should be like 80%, the duty cycle for the blue channel like 20%. And that is the technique for creating a bunch of different colors in your blade. The problem is the frequency itself. Galaxy's Edge lightsaber blades will complete one full period 6,000 times a second, or 6 kilohertz. Mine, in a solid color where the whole blade is one color, it's actually operating at closer to about 1.8 kilohertz. And it looks fine. Even in cameras, it looks fine. But then when I'm controlling the individual segments, things get a little interesting. Because now I'm not just pulsing the LEDs, I'm pulsing each segment. So hundreds of times a second, one segment, and only one segment will turn on. And the colors for that segment will also be turned on. And then that's turned off, and then it goes to the next segment. So only one segment is ever being lit. So this 1.8 kilohertz frequency now gets divided by 4, because in the same amount of time that I would do the whole blade, I now need to do 4 separate segments. So each segment is turning on and off at roughly about 500, or between 4 and 500, maybe 450 hertz. Because there are 4 different segments. Again, we're dividing it by 4, so we get the 450 hertz-ish. The problem is at 450 hertz, that frequency is low enough that it starts to create problems in cameras like you just saw. And if you're out at Galaxy's Edge with a blade like this and it's pulsing those LEDs at such a low frequency, everybody's gonna pick that up on their cameras, and it's just not gonna look very good. Ideally, I want something that's much faster than this. I want my frequency, when I have each segment has its own color, instead of 450 hertz, I want something like 4 kilohertz or even 6 kilohertz or even more than that. So how do I get a faster frequency? That's where the design problems of my PCB come into play. Each transistor hooks up to a pin on the microcontroller, and that pin on the microcontroller will turn these separately on and off. The way I designed this is I wired these transistors, all 7 of them, up to just random pins on the microcontroller that I knew I could control in software, without really thinking things through about the speed or the frequency of the PWM signal. The way the software is designed is that at some regular interval, a function gets called, and that function is going to turn these transistors on and off as needed. And I won't go into too many details. I'm using a overflow interrupt on timer 2. So the idea is you put a number into a register, and then every tick of the microcontroller, it increments that by 1 when it gets to 255, and then it goes to 0 because it's an 8-bit counter. The largest number you can have in 8 bits is 255. When you increment 255, it rolls over to 0. That's called an overflow, and that triggers the function to call to then set these transistors on and off appropriately. There's a lot of overhead in that. And the end result is that the fastest I can get this thing to operate is about 25 kilohertz. Well, that's more than enough for this 6,000 kilohertz I was talking about earlier, right? Except it's not. The way I have my code set up right now is every time that function is called, it's incrementing its own little internal counter, and it's counting from 1 to 8. And depending on how on the color value of red, say you have a color value of 4 on the red channel, well, it'll start at 1. Is 4 the color of the red channel, less than or greater than the counter? Yes, keep that red channel on, turn that red transistor on. It increments to 2, to 3, to 4. Yep, we're still good. The color and the counter are equal, or the color value is equal or greater than the counter. The counter goes to 5. Oh, we've gone past the color value of red. Let's turn off that red transistor. The code is set up so that there are 8 steps or 8 levels of brightness for each color. That means that I need to call that function 8 times in a row before I've completed one cycle of controlling a given color. So that 24 kilohertz, divide that by 8. And now you're starting to look at what the maximum speed that I can get out of this. I get around, as you saw, or as I said earlier, around 1.8 kilohertz out of my function. And then if I divide that by 4, because each 8 cycles is only for one segment, so I'm going through 24 cycles now to cover the whole blade. If each segment gets its own color, well, now the frequency drops again by, gets divided by 4 to the 400-ish hertz, the 450 hertz. That creates those color bands. There are solutions. There are solutions with this specific microcontroller. There are pins on this microcontroller specifically designed to PWM LEDs. And you can set it up in such a way that there's no overhead, and it can go at hundreds of kilohertz, controlling these LEDs, turning them on, the transistors, turning them on and off. I didn't wire up any of these transistors to those PWM pins. So there's one mistake. I should probably try rewiring this to use those PWM pins, at least for the 3 color channels. And then in software I can PWM the 4 segments, and I'll get a good enough result out of that. The other way would be to increase the clock frequency of the microcontroller. I'm using an internal oscillator for this, running as fast as it could at 8 megahertz. But I could get that up to 20 megahertz, so more than double the speed, except that to get that kind of speed, I need to add an external oscillator, which means an extra chip I need to put on the board here. That can operate that speed. There's nothing in the chip that can operate at that speed. I need an external oscillator to make it go that fast. The other problem is, to go that fast, this particular chip needs a higher voltage being pumped into it than the 3.3 volts that I'm currently pumping into it. And pumping up the voltage to 5 volts will add complexity to the circuit. So what I think ultimately is this should be redesigned so that the red, green, and blue channels are hooked up to hardware PWM pins here, and use those to control the colors, and then deal with the PWMing the segments in software, and I think that would have worked fine. But I'm also now looking at a smaller, faster, cheaper microcontroller. Atmel has a whole wide range of microcontrollers. They have an AT Tiny series. In fact, I use a AT Tiny 85 on a bunch of different things. My Savvy's logic board replacement thing that I made a while back when I broke my logic PCB in my Savvy's Workshop lightsaber blade, at its heart is an AT Tiny 85, a tiny little microcontroller. Well, there's a whole new range of these that just came out. And one of them can run up to 20 megahertz using just its internal oscillator. And it's smaller too, which means it frees up more space to do other things. What those other things are, I don't know yet. And it has the same hardware PWM pins that everything else that this microcontroller has. So what I think I'm going to do is I am going to redesign this PCB yet again. And I am going to use a different microcontroller, and I'm going to hook up the red, green, and blue channels to the hardware PWM pins so I can PWM the heck out of that blade, get it going really super fast, and avoid all that color banding that you saw when I was trying to demonstrate my custom blade earlier. But that also means that to make sure I don't run into this problem again, before I redesign this board, I want to breadboard everything. And the microcontroller is so new that the footprint for that microcontroller's pin, or the package, this plastic package that the microcontroller comes in, the new one, so new, the footprint, I can't find anything that converts that footprint to a DIT package that I can then put into a breadboard. So I have to make my own. I have to design my own adapter, which I already have, and I've already put in an order tonight with Osh Park to get a few of those. The microcontrollers, the new ones, are on their way from Mauser. I probably can start looking at redesigning everything, having all the hardware in place. I can probably start working on that maybe 3 weeks from now, 4 weeks from now, once I have everything in hand. Until then, I'm going to keep working with what I have here. The software is good enough that I can test with it at least. And I can work on creating different color effects, like the rocket popsicle that I showed you before, or the unstable effects. I don't know what effects to add, so I'm looking for suggestions of lightsaber blade effects that you would like to see. For example, I've already got a color picker, so you can turn the thing on and it will cycle through the colors, and you can pick what color you want and then turn your blade off and on again, and it will become that color. So that's where things are at. My version 2 board works. Lessons have been learned. On to version 3. I really wanted to do one video about this, just one. Just open it up with a perfectly working replacement controller board and, put the files and the code out there so that people can make their own, and wow, how awesome will that be? But it is not to be yet, but it will.